Hello, welcome. My name is Mr. J.M. Kimani. I welcome you to our lesson 1. Lesson 1 will feature on the introduction of this decision theory and also the environment of decision making. When talk of decision theory, this is about decision making. And of course, decision making is a process of trying to choose the best course of action, the best strategy, the best option, the best action among alternatives. You cannot be making decision if you have only one alternative. You can only be making decision if you have more than one alternative. So that now, with some considerations, you are able to choose the best alternative, and that's what we called decision making. Now, in the process of decision making, there are some of the items that we require to understand. For example, we require to understand about the decision alternatives. Now, these are the choices you have. These are the choices. These are the choices. These are the actions, or what we call the courses of actions. These are the strategies you have. As a decision maker, you require to have several choices. So that now at least we can be able to choose, or you can be able to choose the best of them. And that is what is going to make you achieve your objective, as well as be able to maximize. Then we also have what we call the states of nature. Now, these states of nature are what we call the conditions. The conditions, the events, the circumstances, like that. One distinguishing factor for the decision alternative and the state of nature is that while the decision alternatives, they are controllable by the decision maker, the states of nature are not controllable because they are not within the discretion, are not within the control of the decision maker. Now, they are probabilistic in nature. They may happen or not happen. They may be known or not known. And therefore, they are conditions that may actually affect the process of making decision. But these alternative decisions, they are within your discretion. They are within your control. And you are with the one who is making a choice. And you do have the right of discretion concerning these alternatives. Then we have what we call the outcome or conditional payoffs. Now, assuming that we give example to the alternative decisions as, say, the supply. Now, the level of supply is within our discretion. We are the ones who decide what level to supply. Is it 100 units? Is it 200 units? Is it 300 units, like that? And then you have the demand. Now, the demand level is another item which is not within our discretion. This is from the customers, and we may not be able to control the customers or dictate to the customers what they should buy. And therefore, this becomes a state of nature. Now, while we are comparing the two, this level of supply and this level of demand, of course, there is the outcome, which is maybe the profit or the loss. In this case now, the outcome or conditional payoffs are now the profit or the losses. If, let's say, like the production is higher than the demand, then of course we have the outcome. If the production is less than the demand and you're having a shortage, of course there's an outcome. So that outcome, which in most cases is profit or losses or income or cost, those are what we are calling the conditional payoffs. And they are the ones we normally use to make decision, and therefore we require to be very categorical concerning these payoffs. Then there is the opportunity loss. Now, always, if you make not the correct decision, if you do not take the correct decision, you'll be making lesser than if you were to make the correct decision. So that difference you are having comparing what you are making currently and what you should be making should you have taken the correct decision is what we're calling the opportunity loss. And therefore, for each and every decision, there is always a loss. And that loss is either a positive or either a zero. Meaning, if you make the correct decision, you'll be having no loss. It's just going to be zero. But if you select not the correct decision or the most important decision, then of course you end up making a loss. That difference is what we call the loss. Now, these are some of the terminologies we require to understand in the process of making decision. Now, while you're talking of decisions, you would want actually to know the procedure of making this decision. So we have now the steps in decision making. Steps in decision making. Now, several steps, like the first one is define the problem. Now, this involves defining the problem and even maybe modeling it in an objective function. For example, we can say our problem is, say, to maximize profit or to minimize cost or either to invest. These are some of the problems we may be having in a company or either as a decision maker. You would want to make money. That means you want to maximize profit. You'd want to minimize your cost. And therefore, you are looking at ways how you can minimize the cost. You'd want to invest. So where do we invest? So you'd want to produce. So such are the problems we're having. And we can model that one using the objective function. Then from there, we actually determine, we list maybe the alternatives. We list the alternative decisions. This is what we are calling the causes of action. So we list the causes of actions. Meaning, how do we achieve this objective? For example, like if it's about making profit, what level of production should we actually operate at so that we can maximize profit? What product should we produce so that we can be able to maximize this profit? Where can we invest? What projects are they available that we can be able to invest and we can manage? You have the capacity to invest. Those choices we are indicating here are step 2, that those choices are going to achieve, or they're going to make us achieve the objective function. Then we may not just select an alternative and we start making profit, or either start maybe determining and achieving this objective. We may also list what we list the possible states of nature. These are the conditions. These are the circumstances prevailing. Now, they may actually hinder the process of making decision. They may hinder the objective function, as in to optimize and to achieve the objective may be a problem if we are having these set of natures. Now, these we are calling conditions. We need to list them. For example, maybe the demand is one of the set of nature, and therefore the levels of demand. If you produce more, if the demand is higher, if the demand is lower, the market conditions also may hamper this. For example, like we can have a high market, a lower market, a medium market. We can have the conditions like optimistic, most likely, pessimistic. Those are what we are calling conditions. And therefore, they may affect our making or achieve the objective. And therefore, we need to list them. And from there now, you're able to have some knowledge concerning these two, the alternative decisions and the state of natures. So that now, we are able in number 4 to determine now the outcomes, which are calling the conditional payoff. So you can have here determine the conditional payoffs. Conditional payoffs. Now these are the outcome. If you are to compare these two, alternative decision and state of nature, is a combination. Is if you combine these two, you'll be having the outcome the way I explained here. Now, one thing to note, the possible states of nature may be probabilistic in nature. And therefore, if you do have the probabilities, you also list them. So this one and their probabilities. If you have the possibilities or the probabilities, then you need to list them also. So that is the step 3. So step 4 is determining the conditional payoffs. And that involves calculations when you are making a comparison and a combination of alternative decision and that of the state of nature, we're able to get an outcome, maybe the profit or the loss, like we said there. Then number 5, we can talk of maybe determining the possible models or either mathematical tools. So you can have here select, let's say appropriate, select appropriate mathematical tool. So among maybe many in the model. So we require to determine which approach we are going to use in the making of decision. For example, like we can have maybe it is maybe under the risk, and therefore we can use the decision rule like the EMV, the expected monetary value, the expected opportunity loss. We can have maybe under uncertainty. So there are several that we may choose from, and therefore we are selecting the most appropriate one. So that now we can apply it in number 6. So we can have apply. So apply the mathematical tool. The mathematical tool. So this one now means we apply it in terms of comparison, and we're able to select the one that is maximizing, the one that is making us achieve the objective, and therefore it is important. That's number 6. Number 7, lastly, is now to perform. So this one, apply the mathematical tool. We are supposed to say that and maybe make recommendation and make recommendation. Make recommendation. But again, before we implement this recommendation, we can check what we call the performing. We can perform sensitivity analysis. So perform sensitivity analysis. Now this one is where you determine the what if, or what we call the post optimality test. You look at, supposing that I'm banking on does not happen, and therefore the opposite happens. How much does it affect my decision? That is now the what if, or either the post optimality. So we are looking at how sensitive our decision is, that if something changes, how much does it change? If it's about the profit making, how much does it maybe derail from the actual profit we are expecting? So it's good to have that kind of analysis, so that now you're able to know how far or how the regret we can be able to consider the regret, so that you can be able to maybe contain. So those are some of the steps that are involved in the process of making decision. Now, there are what we call the environments of decision making. We have what we call environments. So this is our environments of decision making. So we have 4 environments of decision making, 4 of them. Number 1 is environment of certainty. Now this environment of certainty is that one where we are presuming that the course of action, the state of nature is known. So this one we normally assume that we have known state of nature, e.g., assuming that we know the demand. We normally assume we know the demand. You can imagine where you are doing the production and you know the demand. That can only happen if it's like an order business where you produce what has been demanded. That time you can be knowing. But if you are doing the normal production where you produce and then wait for the customers, you can never be very certain concerning what the customers are going to order. And therefore, it is a rare environment that not most cases, not often, you may be actually be certain concerning what state of nature, what circumstance, what condition, or what event may occur. And therefore, we do not normally do some calculations concerning it. Then we have number 2 is environment. Environment of risk. Now, environment of risk is where we have unknown states of nature, but it is possible to attach the possibility or the probability. It is possible to attach the probability of the states, probabilities of these states of nature. Out of what? This is out of past experience. Past experience. Meaning that yes, you do not exactly know what state of nature will occur, but in a way, out of the past experience, you can tell what levels or what states may occur and their possibility. You can be able to attach the probability. For example, if you have been in the business and you have been producing, you know the levels of demand that you have been facing. For example, the customers may have ordered 100, may have ordered previously 200, may have ordered 300, like that. So if these are the possibilities, then you already can tell from your past experience from the frequency, and the frequencies are going to give you the probability. So this is something that we are banking on our past experience and something that has enough past data, and therefore you're able to attach the probabilities concerning this state of nature. Then the number 3 is environment. Environment of uncertainty. Now, this environment also we have unknown states of nature, but we have impossibility of attaching probability. So, impossible to attach the probabilities. This is due to lack of past experience or data. So due to lack of past experience or lack of past data. Now this means, is, for example, like we are a new company, is a new product, we have not done it before. And therefore, we can only imagine of the states of nature, like the levels of demand. If, for example, you have never dealt with the product, how do we get to know the levels of demand? The customers can order what quantities. We can only imagine what quantities the customers would order. And it's an assumption that we know those, we can be able to tell those states. But most importantly is that the possibility of every state happening, we are only we can't be able to attach, and therefore it is the main difference between the uncertainty and the risk. That in the risk you are able to attach the probability due to past experience or past data, but for this one, since it's the first time you're doing it, then you do not have the past data, and therefore you are unable to attach the probability. But we normally assume that you can be able to maybe guess what state of nature may happen. That's the difference. Then now we have number 4 is environment. Environment of competition. Competition. Now this is where, under the same environments we're having here, especially the environment of a risk, we normally assume that now you are not alone in the market. There are several rivals or either participants in the market, competitors in the market. And therefore, as much as we are trying to execute like the environment of risk or even that one of uncertainty, as long as you are addressing a case of several competitors, then we have it as environment of and of a competition. Now, this one we normally call it as game theory. Game theory, where we'll be addressing a case of several competitors in the market and making decision knowing that you're not alone. Your decision may affect another competitor positively or negatively. The other competitor may also affect you positively or negatively, and therefore that kind of decision making when you are capturing or either we are minding those players in the market is what we call the environment of competition, and that is game theory. So that is all about the environments of decision making, and we are going to be looking at examples concerning these environments. Now, beginning with the first one, the environment of risk. Remember, the first environment, we don't do any calculations because we are assuming that we know which state will happen, and therefore you just take the best possible decision. But now when it comes to the second one, so here, so this is environment of risk. Now there are two decision rules. So you have decision rules. So we have the first one, Roman 1. We have what we call the expected monetary value. So this is EMV, which is actually summation of XI, PI, which you can say here that, so where XI represents the payoff, PI represents the probability. So expected monetary value, abbreviated as EMV, is given by summation of XI, PI, where XI is the payoff, while PI is the probability. And here we choose decision alternative with the highest expected monetary value. We choose that decision alternative with the highest expected monetary value, EMV. That is our decision. That is the first one. Then the second one is expected opportunity loss. So this one is EOL. Now this EOL is summation of LI, PI, where we can say LI represents the loss, while PI represents the probability. Meaning the loss, the opportunity loss that we may make, we multiply by the respective probability, and therefore we get the EOL. Then our decision here, choose decision with the lowest EOL. So we choose that decision that has the lowest EOL, and therefore that or those two are our main decision rules. We follow the two. Now, one thing to note, the two, they give the same conclusion, and therefore in one question you may not be asked to do both, to do EMV and to do EOL, because they will have the same conclusion. So the same solution is like a duplication, and therefore is either we are using the EMV approach, period, or we are using the EOL approach. In most cases we use the EMV approach. So that is how. Now, for us to understand this, we need to have an illustration so that we can be able to indicate all these. And at the same time, as we look at two decision makers, there is a decision maker who is risk averse and the other one who is risk taker. Now, the one who is risk averse, he may select that decision that gives the highest EMV, like you have said here. And the risk taker or the risk averse, since we have said that he is going to use this decision, let me make it clear. What I mean is, we have the two, risk taker and risk averse. The risk taker does not care about the risk and therefore does not even need to measure the risk. But the risk averse, he has to measure the risk. And therefore, this addressing here, when we say we choose that with the highest EMV, we are imagining we are addressing a case of a risk taker. But for a risk averse, he has to make a decision with respect to the risk. And therefore, how do we measure the risk? So here we have like two ways of measuring the risk. So you can have here measures of risk. Measures of risk. We have two measures. We can have Roman 1. We can have what we call the standard deviation. Standard deviation. So this one, we can say that the sigma equals to summation of x minus x bar squared probability, while the second one, which is coefficient of variation, this is the CV. This one is actually going to be the standard deviation divided by the mean. That is the sigma divided by the x bar. Now remember something. This we had done it in, I think, topic 3, the CVP. We measured the risk. We measured the risk, exactly standard deviation, and also the coefficient. We did a lot in this area. So just to remind you that you can measure risk. Remember how to measure risk is actually taking the summation of the variance, which is the deviation bit from the mean, square times probability. Of course, we have probability, while this one is where we take the solution to this, which is the standard deviation, we divide by that mean, and the mean is now our EMV. To be specific, this x bar actually is the EMV. The only thing is that for that risk averse, he has to measure risk for concerning each and every decision, so that now he can make his final decision. So if you're having like a 2 or 3 decision, he has to measure risk of all of them, so that he can make his final. Just like the way a risk taker is measuring the EMV of each and every decision and choosing the one that has the highest EMV. That's how I would expect concerning the measures of risk. So we need to have an illustration, so for us to understand all these concepts that we have indicated. Now, the illustration reads that the following payoff table represents the net present values for the 3 alternatives of project for the different market states. We have a state of market, we have the diminishing, static, expanding. We have the probabilities for them, 0.4 for diminishing, 0.3 static, and 0.3 expanding. Then there is the projects, project 1, 2, 3. For project 1, their net present values are 100,000, 200,000, and 1 million. Project 2, the outcome is 0, 500,000, 600,000, while project 3, we have 180,000, 190,000, and 200,000. Required, number 1 or number A, advise the company on the optimal decision, and number B, what is the maximum amount the decision maker would be prepared to pay for advance information on which the outcome will occur. The end of illustration is just a simple illustration for you to understand how we work out the EMV and all that. So we'll have this way. Let me erase here. So we already have the payoff table. It's a simple example that we do not need to determine the outcomes or the conditional payoffs. We already have the payoffs. Unlike other questions we are going to do later, that we require to compute and determine also these table. So we are going to have this way, this conditional payoff table. So we do have here the decision, which actually we have been given projects. Then you have the states of nature, which I've read as the state of market. And this state of market, we have been given there diminishing, static, expanding. This is diminishing. We have static, we have expanding. The probabilities we have 0.4, 0.3, 0.3. And then we do have now the outcome, which shall be the EMV. EMV there. The project, we have project 1, 2, and 3. So like now, we have 100,000 here, 0, and you have 180 as per the question. We have 200,000 here for the static. We have 500,000, and you have the 190,000. Then you have the 1 million. We have 600,000, and you do have the 200,000. Now that's what you have. So we have project 1, 2, and 3, and these are the payoffs. These are the net present values. So that we are going to multiply by the respective probabilities. We get now the EMV. So this is the net present value. So this one can only be the expected net present value. So this one is expected net present value. The word expected comes in because of the probability. Otherwise, initially it is just NPV. But this now is expected NPV. Now we are going to just compute, like we have indicated in the formulas there, that we take the payoff, we'll play by the probability. For example, the possibility of, if we select project 1, the possibility of earning 100,000 is when is diminishing, is 0.4. So we'll be taking 100,000 multiplied by 0.4. We add the 200,000. We multiply by 0.3 plus the 1 million. We multiply by 0.3 also. This is going to give us an average of 400,000. Now this is the average outcome between 100,000 the lowest and 1 million the highest. Then when it comes to the project 2, we have the 0 times the 0.4 plus we have 500 times 0.3 plus 600 times 0.3 also. This is going to give us 330,000 as the expected outcome, 330. Then finally, we have the project 3, 180,000 times 0.4. We have plus 190,000 times 0.3 plus 200,000 times 0.3 also. This will give us the 189,000. 189,000. So let me repeat that. 180,000 multiplied by 0.4 plus 190,000 multiplied by 0.3 plus 200,000 times 0.3, giving us 189,000. That's true. Now, we have said that if you're using the EMV, then you are going to choose the best decision, the one that has highest EMV, because these are incomes, they are NPVs. So the highest is this 400. And on that now we'll say here that, So this is now the conclusion that the optimal project, or either the optimal decision, is project 1 with the highest EMV. So the optimal decision is project 1 with the highest EMV, which is true, as the highest. Everybody who is rational will go for that which is giving us the highest. Now, I'm going to address this the way it is asked, and also the part B. Then I also show you something about the risk averse. Now we have the part B, this one being a part A. The part B is asking us the maximum amount you can pay for the optimal, or either for the information. We call it as the value of information, of perfect information, value of perfect information. Perfect information. Now, when talk of value of perfect information, we normally say that this is the maximum amount you can pay to obtain flawless. So to obtain flawless or perfect information. So maximum amount a decision maker can pay maybe to an expert to obtain the flawless or the perfect information. That's what you're being asked. Now, how do we determine that amount? We determine the amount this way. We take the expected value, so this one, so VPI, we take the expected value with perfect information minus expected value without perfect information. So we take the value with perfect and the value without perfect information. Now we can say here that where the expected value with perfect information is given by, if we are informed, then we are supposed to make the correct decision. For example, information is concerning which state of nature should occur. Otherwise, the project is our discretion. We who are making decision, we reserve the right to make these decision. But the information we are obtaining must be what we do not know exactly, which is about this state of nature. Now, suppose we are advised that it is the diminishing state of market that will be in the market. We are, of course, going to choose the one that is going to give us the best. So the project that will give us the best outcome is project 3, giving us 180,000. While if we are informed that it is the state of static that will be in the market, we'll choose the one that is giving us the highest, which is project 2, giving us 500,000. This is the best. And finally, should we be maybe advised that it is the expanding state of market that will find the market, then of course we'll select the one that is giving us the highest, which is 1 million. So we select project 1. Now with this, we now can say here that if we are informed, we have the information, then we'll have the 180,000 multiplied by probability of that diminishing happening is 0.4 plus the 500,000 times the probability of the static happening is 0.3 plus the 1 million multiplied by the probability of expanding, which is 0.3. Now this one will give us an amount of, this is 180,000 times 0.4 plus 500,000 multiplied by 0.3 plus 1 million multiplied by 0.3. This is giving us 522,000. This is 522,000. This is the maximum amount we can ever make if we make the decision when we have the information. Otherwise, expected value without perfect information, this one shall be the best amount we can make on a decision, comparing the first, the second, the third project. If we select one project and we maximize, we are going to take the 400. And remember, why are we saying that 400 is the amount without information? Is because this 400 is made up of all these. Look at these outcomes. 100,000 is not the best when the state is diminishing. The best one would have been 180, meaning we don't have the information. The best is not 200 when the state is static. The best is 500, meaning we also don't have the information. That's why we are saying that even if it seems to be the best as we compare, it does not have the information. Otherwise, if it had the information, we would have chosen the way we have highlighted. Now, with this, what is the expected, what is the value? So you can say, therefore, the value of perfect information, VPI, shall be the 522,000 minus the 400,000. And this is going to give us an amount of 122,000. The value of obtaining information is 122,000. We are going to obtain this information at any cost, as long as the cost does not exceed 122. We must do what we call the cost-benefit analysis. If the value is 122, the cost should not exceed 122. And therefore, we as the company, trying to obtain information from an expert, we are going to engage an expert who is going to charge us an amount which is less than 122. Should not exceed 122. Our profits would increase from 400 to 522, will increase by that 122. Therefore, if we can pay an amount less than 122, then we'll be better off. That's how the question is to be done concerning the part A and part B. But now I would want to expose you to a case of risk averse, the one who is supposed to measure risk and be able to get the decision with the least amount of risk. Now, like I've indicated here, that risk measurements, you measure using the standard deviation and the coefficient of variation. Then if you are to determine this way, like now you can have, this is a project. We can have x minus, so you can have this as, so if you're having project, let's say you're having project 1. So for each project, we have these values. These are the values. And we have other projects. So for example, if you're having, this is like, let's say, it's a project 1, 2, 3. And we have values as follows. Maybe have the x minus x bar. There are several of them. So x minus x bar. We have probability. X minus x bar. The probability. X minus x bar. And the probability. Why I'm doing this is because, like, if you take this project 1 itself, you see it has these 3 values, which we are going to subtract them from we are going to subtract the EMV, and then we multiply the probability and then get our value. Anyway, suppose I do this way. Instead of having all that calculation, suppose I have this. This is my x bar. Then I have x, and this is my probability. But although probability, I have several of them. I have 3 of them. Suppose I'm having now x minus x bar squared, then probability. So for this is 400,000, the EMV. I have 330,000 I have the 189,000. So if I can determine this way, I take like project 1. I have 3 values of x for diminishing, static, and expanding. If I take the first one as 100,000, I subtract 400,000, I get, we have negative 300,000. Now we square it. We square it. Then you multiply by the probability, which is 0.4. This shall give us an amount of, this is this is a standard form. This is standard form. So you can have it there as, this is 36 billion, or this is 36 that way. But you can also add the other one now for 200. So it is going to be 200 minus this 400. We square it. We multiply by the probability, which is 0.3. This also is going to give us, is the standard form. So this is, I can make it in reduced. This is going to be that 6 billion plus 12 billion, and then plus the last one is 1 million minus 400,000. Then you square it, you multiply by probability, which is 0.3. This is going to give us, this is 108 billion. So when you add this, 36 plus 12 plus 108, this is going to be 156 billion. Now the standard deviation of it is square root of that, square root. So if you are to square root, to square this is going to be like 156. You square it, this is square root of, this will get 394, 968. This is the square root you'll get. Then the next one now, you have seen what I'm doing. So the second one is now 0. You subtract 330,000. Then you square it. You multiply by 0.4. This is going to give you an amount of, this will give you, this is 43.56 billion plus. The other one is 500,000 minus, so 500,000 minus this 330,000. You square it, then you multiply by 0.3. This is going to give you 8.67 billion. And the last one is the 600,000 minus 330,000. Then square it, then multiply by 0.3. This is giving us, this is 21.87 billion. So when you add this will give us 43.56 plus 18, or 8 plus 8.67 plus 21.87. This is giving us 74.1. So the standard deviation now of this, so square root of this, so times 1,000, so square root, this is giving us 272. 213. The last one is this 189. So you take 180,000 minus 189,000, which is 9,000. They square it, multiply by 0.4. This will give us This is a 0.324 billion plus. The other one is 190. Or you can just use million for this one. Is small figure. So you can have that 2.4 million plus. The other one is 190 minus 189, which is 1,000 square it times 0.3. This just will give us 300,000. And the other one is 200 minus 189,000, which is 11,000 square it times 0.3. This is giving us 36.3 million. So together, when you add this is 300 plus 32, 400. This will give us 69 million. So which the square root of it is giving us 8307. Look at this now. These are the star deviations. And you have said that we measure the star deviation this way, and you have done it. Now, this being the star deviation, we said that we normally are going to advise. So this is the hint. So choose decision. So choose decision with lowest star deviation and CV, of course. So that in this case, we will choose what? Project 3 that has lowest. This one has lowest. But at the same time, if you are to apply CV, you know it is star deviation divided by the mean. So if you're having project 1, project 2, project 3, what would be the CV? So CV in this case will be, this one is 394, 968. We divide by this mean, which is 400,000. While the other one is this 272, 213. We divide by this 330,000. And the last one is 8307. Divided by this 189,000. So the first one, which is 394, 968. If you divide by 400,000, this will give us 0.99. Then you have 272, 213. Divided by 330,000. This will give us 0.82. Then this is 8307. Divided by 189,000. This will give us 0.04. So again, this is the best. So both the star deviation and the CV approaches, they are actually matching, and they're telling us that the lowest, the project with the lowest SD and CV, which is risk, is the project 3. So you can say here that therefore the optimal project or decision, so let me just indicate the optimal decision. The optimal decision is project 3 with the least, so the least amount of risk. Now this is now for the risk averse. Anyone who would want to avoid risk, then they would want to choose the third project. Now, looking at what we had indicated here, project 1 was the best. Why? It was giving us the highest. The only problem with project 1 is that it has also the highest amount of risk. And it is true and it's normal that the one that is giving us highest profit is the one that has the highest risk. So for a risk taker, he does not mind the risk. So he goes for the highest profit. But for a risk averse, he minds the risk. And therefore, he's not taking the first project, despite it giving us the highest profit, he's taking the number 3, which is giving us a lower profit because it has also a lower risk. And that's what we mean by measurement of risk concerning the project. That is all about that illustration and the solution concerning that. Now, we've come to the end of lesson 1, where we have featured the introduction part of this topic, as well as the environment of risk, which I've indicated. I've shown you the EMV and the value of perfect information, as well as the approaches concerning the risk taker and also risk averse. So like I've told you, the risk averse has to measure risk concerning each and every project or each and every decision, so that he can make his decision with the lowest risk. But the risk taker, he does not mind about the risk. He goes to the decision with the highest expected value, and that is it. Now, in our next lesson, which is lesson 2, we are going to look further into some of the questions that entails decision making under uncertainty, as well as risk. You can have a question that is asking both risk and uncertainty. So you're going to do further examples in the coming lessons. So we meet in the coming lessons. Thank you, everyone.